Welcome again to Engineers Newsletter Live. I'm Jeanne Harshaw from Trane's System and Application Engineering Group, and today we'll discuss ASHRAE Standard 62.1. This course is approved by the U.S. Green Building Council for 2 Green Building Certification Institute continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to GBCI. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare and Sustainable Design Credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, check your state's rules to see if credit for attending today's program can be applied to engineers' continuing education requirements. ASHRAE Standard 62.1 is titled Ventilation for Acceptable Indoor Air Quality. It specifies ventilation rates as well as system design, construction, and operating requirements that will provide acceptable indoor air quality. It's the basis for many local building codes and is a prerequisite for LEED certification. During today's program, Trane Applications engineers Dennis Stanke, Paul Solberg, and John Murphy will take us through a discussion of the requirements of Standard 62.1, with specific focus on the ventilation rate procedure for calculating ventilation requirements. Dennis, who is a longtime member and recent chair of the Standard 62 Committee, will start us off with an overview of this standard. Then the guys will step us through how to use the ventilation rate procedure to determine the ventilation requirement for each zone and how much outdoor air must be brought in at the system level intake. And later, Paul and Dennis will touch on exhaust requirements and discuss various dynamic reset strategies for saving energy required to condition this ventilation air. Since there's so much that could be covered on this topic, we've done something a little bit different for today's program. We recorded supplemental content that will not be aired during the main program, kind of like a bonus feature. We'll make mention of them throughout the program. This supplemental material is included on the DVD, or it can be viewed on demand at our website, trane.com/ENL. Now for the main program. Dennis, go ahead and get us started.
Okay, first I want to thank all of you for watching these presentations. We've been doing them for many years, and I hope that you find them of value. I don't know how many of these I've been involved with, but I'm happy to say that this is my last one. So in case I forget to say it later, I've enjoyed talking to you periodically, and I hope that you continue to attend long after I've retired to New Orleans, for example. Anyway, today I'm going to give you a quick overview of the 2010 version of Standard 62.1. It's a mandatory language ASHRAE design standard with the purpose of specifying minimum ventilation rates which will provide acceptable indoor air quality and minimize adverse health effects. It applies to commercial, institutional, and high-rise residential buildings, but not to healthcare. Its requirements are organized in sections as follows: outdoor air quality assessment in Section 4, provisions for systems and equipment in Section 5, ventilation rates and calculation procedures in Section 6, construction and startup requirements in Section 7, and finally, operation and maintenance requirements in Section 8. Normative Appendix A, which expands on Section 6 requirements, is also part of the standard. The standard is written in mandatory language so that it can be easily adopted by codes and can be used as a solid technical reference document for other standards, for energy labels, and for building rating systems. This diagram attempts to show how the standard fits. First, here's Standard 62 broken down by section. Traditionally, Section 6 is most important for the model mechanical codes and many local building codes. Its ventilation rates and procedures appear in over 11,000 code jurisdictions. To comply with ASHRAE Standard 189.1, the High Performance Building Standard, building designs must meet virtually all Standard 62 requirements. And the International Green Construction Code allows Standard 189.1 as a project compliance option. Projects following this option include all Standard 62 requirements referenced in the Standard 189.1 document. Some building owners want to pursue a building energy label, like Energy Star or the ASHRAE Building Energy Quotient label. To comply with the Energy Star, all 62 requirements must be met. And since the ASHRAE BEQ label requires Energy Star compliance, again, all 62 requirements must be met. And of course, many building projects these days seek LEED certification. The first LEED indoor environmental quality prerequisite requires compliance with the provisions in sections 4 through 7 of Standard 62.1. So you can see this ventilation standard provides the basis for building codes, energy labels, and building rating systems. Okay, back to the standard to give you that quick overview that I promised. Section 4 addresses outdoor air quality. It requires designers to consider potential outdoor contaminants both in the region and immediate vicinity of the building site. Section 5 covers a broad range of requirements for ventilation systems and equipment. When met, these requirements should help to establish a baseline for building contaminant emissions so that the prescribed ventilation rates and procedures in Section 6 can actually be expected to work. These sections cover a lot of ground, so we've included them in the supplemental material since we want to focus on Section 6 today. Turning now to the procedures for finding design ventilation requirements in Section 6, the standard includes 3 alternative design procedures for finding minimum outdoor airflow rates: the ventilation rate procedure, the IEQ procedure, and the natural ventilation procedure. And it includes exhaust airflow requirements in a separate section because they apply regardless of the design procedure used to determine the minimum outdoor airflow rates. The ventilation rate procedure is most widely used. It prescribes zone-level outdoor airflow rates in a table, and it prescribes equations and calculation procedures needed to find both zone and system-level rates. Most designers understand it and use it, and it's the basis for mechanical codes. Of course, it has a few tricky spots, so we'll go over an example a little bit later. Next is the indoor air quality procedure. Designers find minimum zone and system intake rates based on contaminant levels and subjective evaluation, proceeding as follows. First, identify all contaminants and mixtures of concern, sources and source strengths, and target contaminant and mixture concentrations. Second, use mass balance equations, accounting for any air cleaning devices, to find the zone and intake rates needed to control contaminant levels to less than or equal to the target concentrations. Third, in the completed building, use a subjective evaluation in each zone to find zone and intake rates that satisfy occupants, or use the rates found by subjective evaluation in a substantially similar zone in an existing building. Finally, compare the zone and intake rates found using the mass balance approach to those found using the subjective evaluation approach, and use the larger of these rates. Designers must perform both a mass balance analysis and a subjective evaluation to comply with the IEQ procedure. This requires a lot of work, a lot of judgment, and risk, not to mention of variance in from most code authorities. That's why very few one-of-a-kind building designers pursue it, why Standard 189.1 doesn't allow it, and why LEED has traditionally not allowed it. It's probably best suited for buildings with repeated identical designs like retail chain stores. I recently wrote an ASHRAE journal article about the IEQ procedure showing in detail how it might be met. We included a reference to this article in the bibliography, but we're not discussing it in detail today. Finally, the natural ventilation procedure provides for passive ventilation using only natural forces to move outdoor air through the zone. It requires that any natural ventilation system also include a mechanical system designed using either the ventilation rate procedure or the IEQ procedure. A mechanical system is needed to provide outdoor air during those times when the local openings must be closed. To comply, first find how far outdoor air can be expected to penetrate into the occupied zone. This depends on the location of openings and the ceiling height. Next, find the area of the outdoor opening. It must be no less than 4% of the naturally ventilated floor area. Finally, provide readily accessible means for occupants to adjust the outdoor openings and provide controls to coordinate the operation of natural and mechanical ventilation systems. Mixed mode ventilation is required because virtually all naturally ventilated buildings need mechanical ventilation at some point. For example, occupants may close local openings due to rain, wind, heat, cold, outdoor pollution, outdoor noise, and so on. As with the IEQ procedure, we're not discussing the natural ventilation procedure in any detail today. Today, we're focused on the ventilation rate procedure. It covers outdoor air treatment, zone level and system level outdoor airflow calculations, an optional averaging approach to design for varying operating conditions, and an optional control approach to reset outdoor airflow dynamically. Before we turn our attention to ventilation calculations, however, I want to briefly discuss outdoor air treatment. We use outdoor air to dilute and remove indoor contaminants. But since outdoor air itself can contain contaminants, in some geographical locations, the standard requires outdoor air cleaning between the intake and the occupied zone. The ventilation rate procedure requires filters in PM10 non-attainment areas, those areas where the concentration of particulate matter, 10 microns and smaller, exceeds the National Ambient Air Quality Standard. Here's the latest EPA map for PM10 non-attainment areas. At least MERV6 filters are required for buildings in all shaded locations shown in both yellow and red. This shouldn't be a big problem since the air handler probably has a cooling coil with a wet surface, and Section 5 already requires a MERV6 filter upstream of any wet surface device. The ventilation rate procedure also requires filters in PM 2.5 non-attainment areas, those areas where the concentration of particulate matter, 2.5 microns and smaller, exceeds the national standard. Here's the latest EPA map for PM 2.5 non-attainment areas. At least MERV 11 filters are required for systems in the shaded locations. Air handler fans must be selected to provide the required airflow whether the filter is clean or dirty. Finally, the ventilation rate procedure requires 40% efficient ozone air cleaners in non-attainment areas where the average daily maximum 8-hour ozone levels are very high, above 0.107 parts per million. Here's the latest EPA map for ozone non-attainment areas. According to Appendix E, only buildings in Riverside, Kern, Los Angeles, and San Bernardino County in California need ozone air cleaners. But these designations change, so designers should check the EPA 8-hour ozone status for any planned building site. Buildings located in ozone non-attainment areas other than Southern California don't need air cleaners to meet Standard 62, but designers might want to consider using them anyway. After all, breathing ozone is harmful, and besides that, if you're designing a high-performance building, Standard 189.1 requires 40% efficient ozone air cleaners in all ozone non-attainment areas, which includes most of California and many major metropolitan areas throughout the U.S.
As Dennis mentioned, we're only going to focus on the ventilation rate procedure for today's program. This procedure includes both zone calculations and system calculations. First, the outdoor airflow needed in each ventilation zone must be determined based on prescribed rates listed in a table. Then, based on these zone calculations, the outdoor airflow needed at the intake for the entire system must be calculated, using procedures and equations defined in the standard. Paul is going to start out by explaining the zone calculations. Paul?
Standard 62 requires a three-step procedure to determine the outdoor airflow required for any occupiable space, which the standard calls ventilation zone. I'll tell you about those 3 steps and then dive deeper into each one. First, we calculate the volume flow of outdoor air, V sub BZ, that must be delivered to the breathing zone within an occupied space, using the prescribed rate in Table 6-1 of the standard. Next, we determine the zone air distribution effectiveness, or how well the ventilation air mixes in the space, which depends on the location of the supply diffusers and return grills. The standard provides default values in Table 6-2 for different air delivery configurations. Finally, we calculate the volume flow of outdoor air required for the zone by dividing the breathing zone outdoor airflow by the air distribution effectiveness. Before I show an example of breathing zone calculations, I would like to talk about Table 6-1, the minimum ventilation rates in the breathing zone. Standard 62 specifies minimum ventilation rates to both dilute space traditional contaminants to safe concentrations and to satisfy the olfactory senses of the occupants. Occupant satisfaction relates to the perceived intensity of odors and irritants from 2 major sources, the occupants themselves and the building and its furnishings. While the actual relationships are complex, most experts agree that the best simple model for effective dilution of odors and irritants involves summing the outdoor airflow needed for each of these sources. As a result, since 2004, Standard 62 has prescribed 2 ventilation rates for each occupancy category. R sub P, the rate for people sources, and another, R sub A, the rate for building-related sources. This table shows prescribed minimum rates for several occupancy categories. Earlier versions of this standard prescribed only 1 ventilation rate for each category. This single rate accounted for the additive nature of odors and irritants, but did so behind the scenes. For example, the 1989 version of the standard required 20 CFM per person for offices. Behind the scenes, that was 15 CFM to dilute people-related odors and an additional 5 CFM to dilute building-related odors. But these old CFM per person rates penalized high occupant density zones, like conference rooms or theaters and churches. By accounting for people-related and building-related sources separately, the new approach, which some call additivity, results in lower ventilation rates for high-density spaces. Now back to our 3 steps necessary to determine the volume flow of outdoor air for a zone. Let's exercise the first of these 3 steps for zone calculations by using a simple example. In Step 1, we determine the occupancy category for the zone using Table 6-1 and identify the corresponding ventilation rates. This includes 2 components. First, the people source outdoor airflow rate, which is called R sub P and is quantified in terms of CFM per person. And second, the building source outdoor airflow rate, which is called R sub A and is quantified in terms of CFM per square foot. Then we determine the peak population for the zone, P sub Z, and floor area, A sub Z, and solve this equation to find the required outdoor airflow for the breathing zone. Side note here, you can use average population for P sub Z, but that requires knowledge of an occupancy profile. The calculation for this is too long to fit here, but will be included in the supplement at the end of this broadcast. As an example, let's consider a 1,000 square foot office that has a peak population of 5 people. For an office occupancy classification, Table 6-1 requires 5 CFM of outdoor air per person plus 0.06 CFM per square foot of floor area. Plugging these 4 numbers into the equation, we find that the standard requires 25 CFM of outdoor air to dilute the people-related sources plus 60 CFM to dilute the building-related sources. So in total, the zone requires 85 CFM of outdoor air delivered to the breathing zone. Let's look at one example. Again, 1,000 square foot zone, but this time it's a conference room designed for 17 people. The Table 6-1 requirements are the same for a conference room as they are for an office in our previous example. 5 CFM per person plus 0.06 CFM per square foot. When we solve the equation, predictably, the conference room needs the same 60 CFM outdoor air as the office space to dilute the building-related sources. But it needs 85 CFM to dilute the people-related sources due to the higher occupancy. In total, the conference room requires 145 CFM of outdoor air compared to 85 CFM for the office. Okay, back to the three-step zone calculation process. Using the prescribed rates in Table 6-1, we just used equation number 1 to determine the volume flow of outdoor air that must be delivered to the breathing zone. We now move to step 2, the determination of the effectiveness of the zone air distribution, E sub z, which is based on how the air is delivered to the space. E sub z helps the designer to account for ventilation air that is delivered to the space by the diffusers, but bypasses the actual breathing zone. E sub z is simply a lookup. In Table 6-2, the standard provides default values for 10 different air distribution configurations. Here's an excerpt from that table. You can see that it's based on placement of supply diffusers and return grills, and the temperature of the air being supplied. For most zones, air distribution effectiveness will be 1 during cooling operation. During heating operation, it may be less than 1, since warm air tends to float above the breathing zone air or rise quickly through it. In either heating design, the air doesn't perfectly mix in the breathing zone, and therefore doesn't do a good job of diluting contaminants. Now that we know both the volume flow of outdoor air to the breathing zone and the effectiveness of the air delivery system, we can calculate the volume flow of air that must be delivered to the space. V sub OZ is simply the required flow to the breathing zone divided by the effectiveness of its delivery. Going back to our office example, the outdoor airflow that must be delivered to the breathing zone is 85 CFM. During the cooling mode, cool air enters the space through the overhead diffusers and returns through grills in the ceiling. From Table 6-2, we find the zone air distribution effectiveness to be 1. This means that delivering cool air from overhead diffusers is 100% effective at getting the outdoor air into the actual breathing zone. So solving the equation, we find that 85 CFM of outdoor air must be delivered to the diffusers so that 85 CFM makes it into the breathing zone. No air bypasses in this mode. But what about during heating mode? If hot air enters the space through the same overhead diffusers and exits from overhead grills, Table 6-2 indicates that the zone air distribution effectiveness is only 0.8. When supplied and returned overhead, the buoyancy of this hot air will tend to cause some of the air to bypass from the diffusers to the ceiling-mounted return grills. So this system configuration is less than 100% effective at delivering outdoor air from the diffusers to the breathing zones. In the heating mode, we find that 106 CFM of outdoor air must be delivered to the overhead diffusers so that 85 CFM makes it into the breathing zone in this office. In this mode, 21 CFM of outdoor air bypasses the breathing zone altogether. This next slide compares the various methods of distributing air to the zone and how the default values for air distribution effectiveness impact zone outdoor airflows for our office example. First, notice that E sub z for most common configurations is 1. Two configurations that have an effectiveness less than 1 are when hot air is delivered through ceiling-mounted diffusers and it also returns from the ceiling, or when warm air is delivered through diffusers in or near the floor and it returns from the ceiling. However, Notice that if you design the system so that the supply air temperature during heating is less than 15 degrees above the space temperature, and if the diffusers are selected to achieve suitable velocities, you can achieve an air distribution effectiveness of 1, even with overhead heating. This should be the design goal. The only configuration that has an effectiveness greater than 1 is when you deliver cool air using true displacement ventilation. Finally, these last two configurations were added to address systems where the outdoor air is drawn into the room. A common example is a hotel in which the outdoor air is delivered to the corridor and then drawn into the individual guest rooms underneath the door.
So that covers the zone calculations of the ventilation rate procedure. Next, John will explain the system calculations. This involves calculating the outdoor airflow needed at the intake for the entire system and builds on the zone calculations we just reviewed. John?
The ventilation rate procedure of Standard 62 defines 3 ventilation system configurations: single zone, 100% outdoor air, and multiple zone recirculating systems. The procedure for calculating the system-level outdoor air intake flow differs for each of the configurations. But in each case, the system calculations build on the same zone calculations that Paul just explained. In a single zone system, one air handler serves the ventilation needs of one zone. All the outdoor air that enters through the intake is delivered to that single zone. Any recirculated air is merely return air from that same zone. Some examples of single zone systems include packaged terminal air conditioners, classroom unit ventilators, or small packaged rooftops. In a 100% or dedicated outdoor air system, one air handler serves the ventilation needs of more than one zone. Outdoor air enters through the intake and is then delivered to the zones without mixing it with any recirculated air. That is, the dedicated outdoor air unit delivers only outdoor air, not a mixture of outdoor air and recirculated air. Local units then handle the cooling or heating loads within each zone. These local units are typically fan coils, water source heat pumps, small DX split systems, or VRF terminals. Or they might be small rooftop units, chill beams, or even radiant ceiling panels. In a multiple zone recirculating system, one air handler serves the ventilation needs of more than one zone. But in this case, after the outdoor air enters through the intake, it mixes with recirculated air before being delivered to the zones. The most common example is a conventional multiple zone VAV system. Also, for some applications, active chilled beams may require primary airflow that is greater than the minimum ventilation requirement. In that case, if they recirculated air, they are also multiple zone recirculating systems. To demonstrate the procedures for calculating system level intake flow, we'll use this very simple 3-zone example. As I mentioned, for each of the 3 configurations, the system calculations build off of the exact same zone calculations. So for our example, the zone outdoor airflows have already been calculated to be 300 CFM for zone 1, 400 CFM for zone 2, and 500 CFM for zone 3. We'll demonstrate the system calculations assuming operation in cooling mode. So zone air distribution effectiveness is equal to 1 in each zone. But I will mention how the results might change in the heating mode later on. Now, starting with a single zone system. Since all the outdoor air enters through a single intake and is then delivered to one zone, this calculation is pretty easy. For our example, we're assuming that a separate rooftop unit serves each of the 3 zones. According to Standard 62, the required system intake flow, V sub OT, is equal to the corresponding zone outdoor airflow, V sub OZ. So V sub OT equals 300 CFM in the cooling mode for the system serving zone 1, 400 CFM for the rooftop serving zone 2, and 500 CFM for zone 3. Note that if E sub Z is less than 1 during heating mode, the system intake in a single zone system may need to be higher. Now let's move on to the 100% outdoor air system. For our example, we're assuming that a dedicated outdoor air unit delivers conditioned outdoor air directly to all three zones, and a fan coil in each zone provides heating or cooling. In this case, since the ventilation system delivers only outdoor air and no recirculated air, the required system intake flow, V sub OT, is simply the sum of the zone outdoor air flows. So for our example, the intake for this dedicated outdoor air unit needs to be 1200 CFM, or 300 plus 400 plus 500. Now for the multiple zone recirculating system, which is more challenging. For our example, we're assuming that one VAV air handler serves all three zones, and each zone has a VAV box to vary the cooling or heating. The primary air leaving the air handler is a mixture of outdoor air and air that has been recirculated from the zones. All zones receive the same fraction or percentage of outdoor air. As a result, while the critical zone, that is the zone that requires the highest percentage of outdoor air, while it is properly ventilated, the other zones served by the system are overventilated. Therefore, the air that returns from these non-critical zones contains some unused or excess outdoor air. Most of this unused outdoor air recirculates. That's good, and the calculations in Standard 62 give you credit for this unused air. But some of this unused outdoor air leaves the building in the exhaust air streams. In other words, some outdoor air enters the system intake, passes through these non-critical zones, then leaves the building without using up its full diluting potential. Some of the outdoor air brought into the system is wasted because of overventilation in non-critical zones. To account for this, Standard 62 requires the designer to determine the system ventilation efficiency, or E sub V, in order to calculate the intake airflow for this type of system. The ventilation rate procedure includes two methods for determining E sub V. You can either use the default value provided in Table 6-3, or you can calculate it using the procedures outlined in Appendix A of the standard. The default approach is pretty simple, so it takes less time. However, the calculated approach is more accurate and often results in a higher efficiency and lower intake flow, so it may be worth the effort. Here are the steps to determine the required system intake flow for a multiple zone recirculating system. Again, this assumes that we've already completed the zone calculations. The first step is to calculate each zone's outdoor air fraction. Second, we find the uncorrected outdoor air intake, followed by the third step of determining the system ventilation efficiency. And finally, the fourth step, we calculate the required system outdoor air intake flow, V sub OT. We'll walk through these steps using our same three-zone example, with the same zone outdoor air flows already calculated. We'll start by performing these calculations for the cooling mode, so air distribution effectiveness is equal to 1 for each of these zones. Later, I'll show how the results might change in the heating mode. This system includes a central air handler or rooftop unit that mixes outdoor air with recirculated air, and then delivers this primary air to individual single-duct VAV boxes. These boxes vary the airflow delivered to each zone. As a precautionary note, we want to emphasize that this example is not intended to reflect a real-life system. Our purpose here is to demonstrate the calculation methods, so we tried to make the numbers simple rather than realistic. Your bibliography lists a series of articles that Dennis wrote for the ASHRAE Journal. They go through these calculation procedures in detail using a more realistic example. So the first step is to calculate the fraction of outdoor air required in the primary air delivered to each zone. This is called the zone outdoor air fraction, or Z sub PZ. This is the ratio of zone outdoor airflow required to the primary airflow delivered to the zone. The larger the ratio, the richer the concentration of outdoor air required to meet the zone's ventilation demand. In a VAV system, the primary airflow changes as the space load changes. So this fraction is higher when zone primary airflow is lower. Standard 62 comments on this by stating that for VAV systems, you should use the lowest primary airflow that's expected to occur at the design condition being analyzed. Now, the most conservative approach would be to use the minimum airflow setting of the VAV box. That would result in the highest outdoor air fraction. But the standard allows you to use a higher airflow than this minimum setting, if that's what you expect in the zone at the design condition being analyzed. And that would benefit by resulting in a lower fraction. Now, back in 2008, Dennis, Mick Schwedler, and Steve Taylor of Taylor Engineering presented an E&L broadcast that discussed how standards 62 and 90.1 impact the design and control of VAV systems. On that broadcast, Steve shared his process for determining the minimum expected primary airflow when calculating a zone outdoor air fraction. Now, we're not going to repeat that discussion today, but that E&L is listed in your bibliography and can be viewed online if you want to revisit that subject. But for the purpose of today's simple example, we'll just take the most conservative approach and use the minimum airflow setting of the VAV box. For Zone 1, the design primary airflow is 2,600 CFM, and the minimum primary airflow setting is 650 CFM. So the worst case outdoor air fraction from Zone 1 is 0.46, 300 CFM of outdoor air divided by 650 CFM of primary air. Solving for the other zones, we find that the outdoor air fractions vary from 0.46 to 0.5 for this example system. With the zone outdoor air fractions calculated, the second step is to determine the uncorrected outdoor air intake. This is the system intake airflow that would be required if ventilation efficiency was 100%. And it's the amount of outdoor air that actually gets used in the breathing zones. Notice that this equation is basically the sum of the breathing zone rates that Paul described, with the exception of this factor D. The D stands for occupant diversity. For any system that serves multiple zones, we know that all zones won't usually be simultaneously occupied at their design populations. For example, if all the workspaces in an office building are fully occupied, the conference rooms will be empty. This diversity can be accounted for when designing the ventilation system. Now, mathematically, occupant diversity is the ratio of the expected peak system population divided by the sum of the peak populations in all the zones served by this system. Note that this diversity value is multiplied by only the CFM per person component of the ventilation rate, R sub P, not the CFM per square foot component. So calculating occupant diversity for our example, the peak population for Zone 1 is 30 people, 40 people for Zone 2, and 50 people for Zone 3. So the sum of these peak zone populations is 120. Based on the expected peak population of 80 people for the overall building, the occupant diversity factor is 0.66. With diversity calculated, next we'll sum the breathing zone rates. The people-related component of the breathing zone airflow is the CFM per person rate times the peak zone population. The sum of these three zones is 600 CFM. But again, that portion is reduced by multiplying by occupant diversity. The building-related component is the CFM per square foot rate times the floor area. The sum for these three zones is also 600 CFM. But again, this is not affected by occupant diversity. Adding these two components together, the uncorrected outdoor air intake is 1,000 CFM for our example. Okay, so far we've calculated the zone fractions and the uncorrected intake. The third step is to determine the system ventilation efficiency. As I mentioned, you can either use the default value provided in Table 6-3 or calculate it using Appendix A. We'll start by walking through the calculation procedure from the appendix. Then later we'll compare those results to the default method using this table. Calculating system ventilation efficiency is a three-step process. First, we determine the average fraction of outdoor air in the system, or X sub S. This is the uncorrected outdoor air intake we just calculated divided by the total system primary airflow. Then we calculate a ventilation efficiency for each zone. For systems with a single recirculation air path, calculating zone ventilation efficiency is fairly simple. For those systems with a secondary recirculation path, more assumptions and calculations are involved. But once the zone ventilation efficiencies are known, the final step of determining system ventilation efficiency is easy. It's simply equal to the smallest zone ventilation efficiency. For step 3A, to calculate the average outdoor air fraction, we need to know the total system primary airflow, or V sub PS. Appendix A defines system primary airflow as the sum of the zone primary airflows. However, for a VAV system, the maximum airflow delivered by the supply fan, often called the block airflow, is less than the sum of the peak zone airflows because of load diversity. This block airflow can be obtained from load calculation software or by assuming some load diversity factor. For our 3-zone example, load calculation software determined that the peak or design airflow for Zone 1 is 2,600 CFM, 3,400 CFM for Zone 2, and 4,000 CFM for Zone 3. The sum of these peak zone airflows is 10,000 CFM. However, the software also calculated the block airflow for the system to be only 6,000 CFM, again due to load diversity. To complete step 3A and find the average outdoor air fraction for the system, we divide the uncorrected intake, which we calculated to be 1,000 CFM, by the total primary airflow for the system, which is 6,000 CFM. So X sub S is equal to 0.17. Step 3B is to calculate ventilation efficiency for each zone. This represents how efficiently the system delivers outdoor air from the system level intake to each individual breathing zone. As I mentioned, this calculation is simple for systems with a single recirculation air path, but more involved for systems with a secondary recirculation path. Hey Dennis, can you give us some examples of systems that might use either of these two approaches?
Well, in a system with a single recirculation path, all the air supplied to each zone is a mixture of first pass outdoor air and system level recirculated air. No air recirculates locally. Single duct VAV systems are probably the most common example. In these systems, the VAV terminals include a primary airflow sensor, an air modulation damper, and possibly a heating coil. Other less common examples of single path recirculation systems are dual duct systems that use a single supply fan, constant volume reheat systems, and multi-zone systems. The single duct VAV system that we're using for our example has a single recirculation air path. Again, all the air supplied to each zone is a mixture of outdoor air and centralized recirculated air. As John explained earlier, Standard 62 gives you credit for the unused or excess outdoor air that recirculates from non-critical zones. In a system with a secondary recirculation path, some of the air supplied to each zone is recirculated from other zones without directly mixing with first pass outdoor air from the intake. For example, fan-powered VAV systems use VAV terminals that recirculate air from the ceiling plenum. And two-fan dual-duct VAV systems recirculate air from all zones through both the heating air handler and the cooling air handler. In a series fan-powered VAV system, one air handler brings in outdoor air at a central location and mixes it with air recirculated from all zones before delivering it as primary air to all zones. In addition, each VAV box recirculates air from the ceiling plenum, providing a secondary recirculation air path. Standard 62 calculations result in a credit for excess unused outdoor air in the recirculated air, whether that recirculation occurs centrally or locally. In a dual fan, dual duct system, the cooling air handler brings in outdoor air at a central location and mixes it with recirculated air from all the zones before delivering it down the cold duct. The heating air handler conditions only recirculated air before delivering it down the hot duct. Both of these airstreams contain some excess outdoor air that has been recirculated from overventilated zones. So the calculations in Appendix A give you credit for this. Now, we're not taking time during today's program to walk through the steps for calculating zone ventilation efficiency for systems with more than one recirculation path. However, we did record that content, so you can review it at another time if you like. You can find it as supplemental material on the DVD or view it on demand at our website.
Okay, getting back to our example. Step 3B for this system is easy because it only has a single recirculation path. So the equation for zone ventilation efficiency is 1 plus X sub S minus Z sub PZ. We just calculated X sub S to be 0.17, and we calculated Z sub PZ for each zone earlier. So solving this equation, we find that the zone ventilation efficiencies vary from 0.71 in zone 1 down to 0.67 in zone 3. Step 3C is to find system ventilation efficiency, which is simply the worst case or lowest zone ventilation efficiency. For our example, that's 0.67, the ventilation efficiency for zone 3. Okay, we're almost there. Now, with system ventilation efficiency calculated, the final step, step 4, is to calculate the required system outdoor air intake flow, or V sub OT. This is calculated by dividing the uncorrected outdoor air intake, which we found earlier to be 1,000 CFM, by the system ventilation efficiency. So for our calculated efficiency of 0.67, the required outdoor air intake for our example system is 1,490 CFM. That is, in order to deliver 500 CFM of outdoor air to zone 3, which is the critical zone, Standard 62 requires bringing in 1,490 CFM at the air handler. Zones 1 and 2 will be overventilated at this condition, receiving more outdoor air than the standard requires. Now that we've calculated system ventilation efficiency and intake airflow using Appendix A, let's look at the default method using the lookup table in the standard. As I explained earlier, you can use either Table 6-3 or Appendix A to determine system ventilation efficiency. Outside of Step 3, however, all the other steps are unchanged. Here's an excerpt from Table 6-3. It lists the default values for system ventilation efficiency based on the largest zone outdoor air fraction, Z sub PZ. For our 3-zone example, recall that the largest zone fraction was 0.5. By interpolating in this table, we find system ventilation efficiency to be 0.65. Note that example 6-J in the standard 62.1 user's manual clarifies that interpolation is allowed when using this table. And it's worthwhile doing because it results in a higher value for system ventilation efficiency. But one important thing to notice about this table: if the largest zone outdoor air fraction is greater than 0.55, Standard 62 requires you to use the calculation method in Appendix A. For our example, using the default value of 0.65 for system ventilation efficiency, the required outdoor air intake would be 1,540 CFM. So in this case, using the calculations in Appendix A resulted in a system intake airflow that is less than what would have been required if we used the default from the table. Note that the default values in Table 6-3 assume an average outdoor air fraction, X sub S, of 0.15. So for systems with a higher average fraction, like our example, using Appendix A will result in a higher system ventilation efficiency and a lower intake airflow. I mentioned earlier that I would discuss the impact of heating mode versus cooling mode. As Paul explained, when delivering warm air to the zone, some configurations have a zone air distribution effectiveness less than 1. So we used our same example to see how an effectiveness of 0.8 would impact the system intake airflow. An E sub z of 0.8 during the heating mode results in a higher zone outdoor airflow, and therefore a higher outdoor air fraction. In our example, the worst case fraction increases to 0.63 compared to 0.5 in the cooling mode. With this high fraction, Table 6-3 cannot be used. So using Appendix A, we find that even though the zone outdoor fractions are higher, X sub S is also higher because the system primary airflow is lower. In our example, this results in a higher system ventilation efficiency and a lower intake airflow. I calculated the outdoor air intake to be 1300 CFM during the heating mode, compared to 1490 CFM in the cooling mode. But it's really hard to generalize this for all applications, so it depends on what the system primary airflow is when the zones are in heating. And of course, if the system is designed so that zone air distribution effectiveness is 1 when heating, this comparison isn't even an issue. By now, after all these calculations, you may be thinking that you should create a spreadsheet to save some time in your next design. Well, ASHRAE thought the same thing, and they include a spreadsheet tool when you purchase the Standard 62.1 User's Manual. So you don't need to create your own unless you really want to. In addition, the ventilation rate procedure calculations have been built into Trace 700. So if you use this tool for load calculations, you've already entered the zone level detail needed to calculate zone outdoor airflows. And with just a few more inputs, it can perform the system ventilation calculations too. To wrap up this section on system calculations, let's compare the calculated intake airflows for all 3 system categories listed in the ventilation rate procedure. For our example 3-zone building, the individual single-zone systems deliver 300, 400, and 500 CFM respectively, for a total of 1200 CFM for the overall building. The 100% outdoor air system delivers 1200 CFM to the building also. And the single-path VAV system delivers 1490 CFM. Although we did not go through it during the program, as Dennis mentioned, we did record a supplement during which we walked through the same example for a Series Fan-Powered VAV system. As you can see, the impact of ASHRAE 62 giving credit for unused outdoor air in a secondary recirculation path can be significant, reducing the intake airflow in this example to 1180 CFM. Now, I think it's worthwhile to point out that to compare the performance of these different ventilation systems, you need to focus your attention on the calculated intake airflows, V sub OT, not on system ventilation efficiency. The reason I say this is that many people erroneously think that a dedicated outdoor air system has 100% ventilation efficiency. Based on that, you would conclude that a dedicated outdoor system brings in 33% less outdoor air than the single-path VAV system, since its ventilation efficiency is 67%, and 15% less than the Series Fan-Powered system. But when you compare the calculated intake airflows, 1200 CFM versus 1490 for the single-path VAV, the difference is only 19% for this example, not 33%. An intake airflow for the Series Fan-Powered VAV is actually a little less than for the dedicated outdoor system, not more. Why the difference? Well, it's because ventilation efficiency of a dedicated outdoor system is usually less than 100%, but it's just not necessary to calculate it as part of the ventilation rate procedure. As defined by Standard 62, system ventilation efficiency is the sum of the outdoor airflows required in all the breathing zones, V sub OU, divided by the outdoor airflow that enters through the system level intake, V sub OT. For most dedicated outdoor air systems, the intake airflow is equal to the sum of the zone outdoor airflows, each of which is based on peak zone population, with no credit for system-wide population diversity. As a result, system intake airflow is based on all zones being at peak population simultaneously, even though that's typically not the case. So for our 3-zone example, The required outdoor air intake flow is 1200 CFM when using a dedicated outdoor air system. Remember that the uncorrected outdoor air intake for our example building was calculated to be 1000 CFM. Therefore, the ventilation efficiency for this dedicated outdoor air system is actually 83%. While we're on this topic, what about single zone systems? When you just look at each system individually, system ventilation efficiency is 100%. But if you're comparing the use of 3 separate single zone systems to 100% outdoor air or a multiple zone system, you really should look at the overall building when making the comparison. For our 3-zone example, the total outdoor air intake flow for these 3 systems is 1200 CFM. Again, with an uncorrected outdoor air intake of 1000 CFM for this building, the combined system ventilation efficiency is 83% when using single zone systems. So when comparing the performance of these different ventilation systems, you need to compare the calculated intake airflows, not system ventilation efficiency. Even though ventilation efficiency is typically not 100% for these other systems, it's not calculated as part of the ventilation rate procedure in ASHRAE 62.
So that completes our step-by-step walkthrough of the ventilation rate procedure calculations when designing a system. Before we move on to discuss how to control the system during operation, let's briefly discuss the exhaust system. Paul?
Through a recent addendum, the exhaust airflow requirements were moved to a separate section, Section 6.5, since they apply regardless of the design procedure used. This is clarified in Section 6.1, which states that the exhaust requirements must be met regardless of whether the ventilation rate, IAQ, or natural ventilation procedure is used. This section contains a table that includes minimum exhaust rates for space types where specified contaminants are generated. Here's an excerpt from that table. The intent is to remove these contaminants at the source by exhausting them directly. For example, an art classroom in a school must be designed to exhaust 0.7 CFM per square foot of floor area. Note also that the exhaust requirements for toilet rooms are based on the number of water closets or urinals. Another nuance of this section is that the makeup air, that is the air that replaces the air being exhausted, can be comprised of outdoor air, recirculated air, or air transferred from another ventilation zone. This provides flexibility for the designer. Okay, let's turn the page now and talk about dynamic reset. Standard 62.1 explicitly permits dynamic reset of intake airflow as operating conditions change. While implementation details are sketchy, the dynamic reset option is clear. Any system control approach that responds to varying conditions is allowed, provided it supplies no less than the outdoor airflow currently required in the breathing zone. Although it doesn't require any specific approach be used, the standard describes 3 possible dynamic reset control options. Zone outdoor airflow may be reset in response to variations in zone population. This option is called demand control ventilation, and there are many different ways to do it. System-level intake flow may be reset in response to variations in system ventilation efficiency due to changes in zone airflow. This option has been called ventilation reset control in the past, but Standard 90.1 calls it ventilation optimization control. Finally, the minimum primary airflow setting for VAV zones may be reset in response to variations in system intake airflow, which occur during economizer cooling operation. This option reduces reheat at the VAV boxes. Today, Dennis will talk about first 2 approaches, and remember, although the standard mentions 3 dynamic reset approaches, it doesn't prevent designers from using others.
Okay, the first dynamic reset approach we consider is demand control ventilation, which usually applies at the zone level. Standard 62 permits it in any zone, but Standard 90.1 currently requires it in zones with 40 or more people per 1,000 square feet. And Standard 189.1 requires it in zones with 25 or more people per 1,000 square feet. When used, the zone level demand control option must meet some simple requirements. First, the controls can't reduce zone outdoor airflow to a value that's lower than the area outdoor air rate for the zone, regardless of the estimated population. Second, the controls must provide the minimum outdoor airflow calculated for the estimated zone population at steady state. This allows designers to ignore the dynamics associated with population variations and damper modulation. Third, when the mechanical cooling system is dehumidifying, the intake airflow cannot be reduced to a level that's lower than the coincident exhaust airflow from the system. This requirement indirectly addresses building pressure. And finally, all assumptions must be documented, including a table showing minimum and maximum outdoor airflow for each zone. Actually, to keep a building at positive pressure when cooling, you'd want the intake rate to be no less than the exhaust rate plus the exfiltration rate, even though the standard doesn't go into that kind of detail. But let's move on. Since outdoor air demand varies with population, one way to implement demand control ventilation involves estimating the current zone population. Current population can be estimated in several different ways. For instance, a time of day schedule in the building automation system could be used to estimate population at any given time. This approach is probably not very accurate, but it can work in zones where occupancy is more predictable, like classrooms or cafeterias or churches. Simple binary occupancy sensors can estimate zone population too. A motion detector, for instance, could be used to indicate either design population or zero population. This all or nothing approach may or may not be such a good idea in some zones, but it can be used successfully in zones that are unoccupied periodically, like individual offices, small conference rooms, some classrooms, and so on. Finally, people can actually be counted in some zones. For instance, theater ticket sales or store entry-exit turnstiles can be used to find a fairly accurate estimate of population. Other people counters are also available, but they are usually more expensive. The estimated breathing zone outdoor airflow currently needed can then be calculated using the estimated population. Alternatively, the breathing zone rate can be estimated more directly using CO2 sensors and a simple controller. Since people produce CO2 at a predictable rate, the difference between indoor and outdoor CO2 level has been widely used to estimate ventilation rate per person. And combined with a simple controller, this difference can be used to estimate breathing zone outdoor airflow. I'll show an example next, but first remember this. Differential CO2 alone can't be used to find current zone population. To estimate population, you'd need to sense outdoor airflow as well as CO2 level, then solve a differential equation to find the current population. Most designers don't do that. For single zone systems and for 100% outdoor air systems with modulated airflow, the difference between breathing zone CO2 and outdoor CO2 level at steady state equals the volumetric CO2 generation rate per person divided by the breathing zone outdoor airflow per person. Typical adults engaged in routine office work generate CO2 at a rate of about 0.0105 CFM per person. Both population and required outdoor airflow rate are unknown, but they are related by the CO2 generation rate. So a simple controller based on this relationship can be used to estimate the current breathing zone outdoor airflow required based on the difference between zone and outdoor air CO2 levels. We can design a controller for each demand control zone as follows. Let's consider a 1,000 square foot lecture classroom with a peak population of 65 occupants. A proportional controller, like the one shown in the 62.1 user's manual, can be designed by simply finding the breathing zone outdoor airflow required at peak population and at zero population. This example zone needs 550 CFM of outdoor air when all 65 people are present, but it only needs 60 CFM when the zone is unoccupied, but the ventilation system is still operating. We use the steady-state CO2 equation to find that differential CO2 at peak population rises to 1,240 parts per million, but drops to zero at zero population. These values define the endpoints for a simple proportional controller. The controller itself is simply a straight line between these 2 points. As population changes, differential CO2 changes, and the controller indicates a corresponding change in estimated breathing zone outdoor airflow. This corresponds to a change in required outdoor air intake flow for both single zone systems and demand control zones in 100% outdoor air systems, and it can be used to modulate outdoor air dampers directly in those systems. Modulating the outdoor air damper, of course, changes the differential CO2 level and estimated outdoor airflow rate. The controller uses the new CO2 difference to modulate the outdoor air damper until the outdoor air rate balances with the sensed CO2 difference. The population is still unknown, but the estimated intake airflow equals or exceeds the minimum outdoor airflow rate actually required in the breathing zone. The bibliography includes an ASHRAE journal article that describes several similar controller designs, and the 62.1 user's manual shows a proportional controller very similar to the one discussed here. We also covered this topic in the 2005 Engineers Newsletter Live broadcast that's listed in the bibliography. Zone level demand control can be used in multiple zone systems too. In fact, to comply with energy standards, systems might need to provide both zone demand control and ventilation optimization control. We'll come back to zone level control in a minute. First, let's discuss ventilation optimization control, which is one of the dynamic reset options specifically allowed by the standard. Used primarily in VAV systems, it's a strategy that recalculates system-level intake flow as system ventilation efficiency varies due to changes in zone airflow. A typical VAV system is designed to bring in at least the minimum intake airflow required for proper ventilation of the critical zone. Remember, the critical ventilation zone needs the richest mixture of outdoor air in its primary airstream. In a properly designed system, all non-critical zones get excess outdoor air at design conditions. At any part load conditions, if design intake airflow is maintained, all zones, including the critical zone, are overventilated. So Standard 62 permits the dynamic reset of outdoor air intake as operating conditions change without even considering population changes. Since each VAV controller knows its required outdoor airflow rate and senses its primary airflow, the building automation system can collect this zone information and solve the multiple zone system equations to find the current intake flow required. This becomes the new set point for outdoor air intake flow at the air handler, and that is how ventilation optimization control works. We've discussed this dynamic reset option extensively in previous ENLs and in the ASHRAE journal articles listed in the bibliography, so we're not presenting details today. In summary, VAV systems work like this. If designed for worst-case intake airflow, system ventilation efficiency always rises from its lowest value at design to higher and higher values as the zone primary airflows drop at part load. Efficiency rises because less unused outdoor air exhausts from the system. And since they are inversely proportional, as system ventilation efficiency rises, outdoor air intake flow drops. Now, can zone level demand control be combined with ventilation optimization control? Of course. In fact, they must be combined in some cases to comply with energy standards. Here's how it can be done. If some zones use a demand control approach to estimate population, such as time-of-day scheduling or occupancy sensors, it's pretty easy. Use design population in zones without demand control and estimated population in demand control zones to find estimated breathing zone outdoor airflow. Use measured primary airflow for each zone and the estimated breathing zone rate to find the outdoor air fraction. Then at the system level, using current information from the zones, solve the multiple zone system equations to find the outdoor air intake flow currently required. But what if some of the demand control zones use CO2 sensors to estimate the required outdoor airflow rather than population? In this case, the design path changes a little. Use peak population in zones without demand control and use estimated population in demand control zones that estimate population. Use estimated breathing zone outdoor airflow for CO2-based demand control zones, found based on sensed CO2 and the simple controller previously described. Note that using the simple controller for CO2-based demand control zones might result in some overventilation because in addition to CO2 from outdoors, the primary air also contains CO2 from people in all other zones in the system. If you choose this approach, be sure to combine it with occupancy sensors in the demand control zones. That way, unoccupied zones with elevated CO2 levels won't be overventilated by mistake. As before, use these zone values to solve the multiple zone system equations for the current system outdoor air intake flow. And finally, set an upper limit on intake airflow. Calculations based on estimates can't result in a current intake airflow that exceeds the design value. After all, cooling and heating capacity are based on design outdoor airflow rates. The best approach for CO2-based DCV zones in VAV systems might require a CO2 sensor in both the breathing zone and the primary air supplied to the zone. ASHRAE research to study this is currently nearing completion, so watch for journal articles about it within the next year. To meet Standard 90.1 and Standard 189.1, high occupant density zones must include demand control in some form, regardless of the ventilation system type. Single zone systems can estimate population to calculate both the breathing zone and the required intake outdoor airflow, or they can use CO2-based controls to establish the breathing zone outdoor airflow and to calculate the required intake airflow. Like single zone systems, demand control zones in 100% outdoor air systems can either estimate population and calculate zone outdoor airflow, or estimate breathing zone outdoor airflow using CO2. But the outdoor air distribution system must be VAV, and every zone in the system must include a pressure-independent VAV box to maintain proper outdoor airflow as the demand control zones modulate their outdoor air flow. Multiple zone systems are likely to be required to use ventilation optimization controls. In addition, they might be required to use demand control ventilation in densely occupied zones. Demand control can either estimate population and calculate breathing zone outdoor airflow, or estimate breathing zone outdoor airflow based on sensed CO2 level. In either case, the current outdoor air value for each demand control zone must be used by the ventilation optimization controls to find the current outdoor air intake flow required for the system. Now, let me summarize dynamic reset. Some single zone systems must include demand control ventilation to meet energy standards. We know how to provide it, and it saves energy with minimal impact on first cost. And if any zone in a 100% outdoor air system requires demand control to meet these standards, its outdoor airflow varies, so the air handler can't supply outdoor air at constant volume. The outdoor air supply must be VAV, and as I just mentioned, every zone in the system must include a pressure compensating VAV box to maintain proper outdoor airflow. We know how to do this too, and it saves energy, but it increases first cost. Remember, the standard doesn't allow population diversity credit in single zone or 100% outdoor air systems, so the equipment must be sized for worst case intake airflow, assuming each zone is at peak population, whether the system includes demand control zones or not. I know it's pretty bad when a quick summary takes 2 slides, but multiple zone system designs account for system population diversity, which saves first cost. They may include dynamic reset at the zone or system level to meet standard 62.1, but they must include ventilation optimization control to meet standard 90.1. And if any zone in the system requires demand control ventilation to meet the energy standard, local demand control ventilation can be combined with ventilation optimization control. The result is a multiple zone system with zone level demand control that really works. That's it.
Well, we hope you learned a lot about ASHRAE Standard 62.1 today. As mentioned, there are a number of publications available that provide more information on the material we covered, including the series of ASHRAE journal articles that Dennis wrote. A bibliography detailing these resources is included in your handout. And don't forget about the supplemental content we recorded. Dennis recorded a segment where he explains all the requirements in sections 4 and 5 of the standard. Paul explains how the standard allows for design based on average population and walks through a few examples. And John expands on his 3-zone example by going step by step through the Appendix A calculations for systems with a secondary recirculation path. The supplemental material is included on the program DVD, or you can view it on demand at our website at trane.com/ENL. As always, past broadcasts are also available on DVD, and many are available on demand free of charge. Visit trane.com/continuingeducation for a complete list of on-demand courses available to satisfy credentialing requirements. Many of them, including this one, are LEED specific. And remember to fill out a survey and let us know how we're doing. AIA members, please remember to turn in your member information to your local site coordinator. And finally, please join us for the remaining Engineers Newsletter Live programs this year. In spring, we'll present single-zone VAV systems, and we'll return in fall to present variable speed chiller plant operation. Thanks for joining us today, and we'll see you in spring.